in the cloud. Great. So now I'm recording that in the cloud, and I'm sharing. What is this? Okay, I'm sharing that screen now. What are we going to do? We're going to state the problem because now we're going to work with something real. Okay. So what is this? What we are going to do today? First, we're going to work with the air handling unit. So now we're working with an air handling unit. Okay. So there will be an air inlet. So there's a duct for the air inlet, and then we are going to heat up this air, and there will be an air outlet. And what do we have in the middle? In the middle, there will be a heating coil. We explained what a coil is last time. Okay, so there's a heating coil. So the heating coil, we have a hot water inlet, and there is a warm or not as hot water outlet. Okay, so this is the heating coil. We have this heating coil. The air goes through the heating coil, and we have water in this coil. So as the air goes through the coil, the air heats up and the water cools down. This is what we want to say here. And this coil is connected to something. To what? Okay, so we can connect this coil with a burner, let's say. It can be gas, it can be oil, can be pellets, whatever. But when we have a burner, we need something to release the air. Okay, the gas. This is the exhaust gas, and we need to release it. And what else? Well, we have this air handling unit. So this is an air handling unit, and this air handling unit is providing fresh air to the room. Okay, so let's there will be a building here. Okay, but this building, there will have, or there will be a window. Okay, so it's not just a wall or a roof. There will be windows here, and as we have the thermal envelope, so we need a kind of thermal insulation here all around the building. There you go. Okay, but we have a weakness, which is the window there. And what do we have in our building? Well, we need people. Okay, so there will be people here practicing an activity. Okay, so there will be different people, and those people will be just moving, sweating.
Fernando, is that you and me having a party?
Yeah, it's but who are you? And who is me? I don't know.
I'm the tall one.
You're the tall one. Okay, this one. So I will.
Yeah.
Okay, so we can say M and S. Perfect.
Thank you.
Okay. So people are moving, are sweating, are having fun, whatever. What's the problem? So we are releasing a lot of moisture to the air. So we need to get rid of this. So that's why we need the air handling unit, because we need to remove the excess of moist that we have in this room, and we need to provide the room with fresh air. Okay, that's perfect. So what's next? Okay, we need the outdoor conditions, the outdoor and the indoor conditions. So imagine that it's cold outside. If it's cold outside, this can be 30 Fahrenheit. And what is the relative humidity? Can be, let's say, 60%. So in winter, the outdoor conditions, we can have 30 Fahrenheit and 60% of relative humidity. What are the indoor conditions? So in indoor conditions, we need comfort. So comfort conditions, it's always something close to 70 Fahrenheit. And let's say that the relative humidity is 45%. Okay, so everything between 68 and 74 Fahrenheit is comfort. Everything between 40 and 60 relative humidity is comfort as well. So those are the indoor conditions, and those are the outdoor conditions. So the air that is going through the air handling unit, so the air intake of the air handling unit, it's at this condition. And the air outlet of this air handling unit has to be at these conditions. Okay, so then we have the heating coil. So with the heating coil, we can heat up, or we move the air from 30 Fahrenheit and 60 Fahrenheit and 60% to 45 Fahrenheit and no 70 Fahrenheit, sorry, and 45%. Okay, so this is the problem. Now, what is the question? We need to know what is the heating or the heat, the energy that they have to provide to this heating coil to achieve these conditions. Okay, so this is a real problem. And we can solve this problem by using the psychrometric chart that we used last time. Okay, so now I'm going to stop sharing that screen, and I'm going to share this one. There you go. And we have this tool, the amazing psychrometric chart, flycarpet.net for free. What do we have to do here? Okay, so here we have to identify the indoor and the outdoor conditions. So what were the outdoor conditions? Outdoor conditions were 30 Fahrenheit. So the dry bulb temperature was 30. The relative humidity was 60. There you go. Now we submit. Okay. And this is, we have to look at two values. We have to look at the enthalpy. Here we have the enthalpy. It's 9.4. And we have to look at the specific volume. I told you that specific volume, it's not always the same, but it's always between 12 point something and 13 point something. Okay. So this is the point. We are in winter, so outdoors we have 30 Fahrenheit, cold. The relative humidity, the outdoor relative humidity is 60. So that means that it's not raining a lot. It's humid, but it's not raining or snowing, because if it were raining or snowing, the relative humidity would be 90, 85, 90. Okay, 60 Fahrenheit, it's, yeah, it's something usual in winter, but it's not raining. But we need to we need to write down this. The enthalpy is 9.4. Okay, so the outdoor enthalpy is 9.4 BTU per pound. Those are the outdoor conditions. The indoor conditions are 70 Fahrenheit. So here I type 70, and relative humidity is 45. 45. I submit again. Okay, so now the point is here, 70 Fahrenheit, and relative humidity 45. We need to look at the enthalpy. The enthalpy is 24.5 BTU per pound. Okay, so this is 24.5 BTU per pound. And the specific volume is 13.5. So the other one was 12 point something. This is 13 point something. So we can use the average, about 13. Okay, so if we use 13 as specific volume for all these exercises, we are good. So it would be, can be 30 point something or 12.85. But if we use 13, 13, we're good. Okay, so now we have to calculate the heating load. Oh, there's something else that I forgot. It's the ventilation load. Hmm. Ventilation load. So the ventilation load, this is a value that it's specified, for example, in the ASHRAE. Okay, so the ASHRAE, I told you.
Anything.
You can't see. Okay, thank you.
Oh.
Good. There might be something wrong here. What about now?
Oh, better. Yeah.
Okay, thank you very much, Monique. Okay, so we have the ventilation load, and I told you that the ventilation loads for different buildings, it's a value that it's specified in the ASHRAE. Okay, so the ASHRAE handbook is the source or the official source that specifies. But I want you to remember something. I want you to remember something very easy. Remember, just a figure. So in most buildings, the ventilation load is always 20 CFM per person. Okay. Sometimes would be 15, sometimes would be 18, and sometimes would be 25. But 90% of buildings, if you use 20 CFM per person, we are good. What does CFM stand for? CFM stands for cubic feet per minute. Okay, so the ventilation load, it has to be 20 cubic feet per minute per person. So imagine that in our building, the building that we saw before, we have like 10 people. So that means that the total ventilation load would be 10 times 20 CFM equals 200 CFM. Okay, so we have 10 persons divided by or multiplied by 20 CFM per person, so equals 200 CFM. Okay, so this is it. CFM, we can write CFM, cubic feet per minute, like this, or we can write CFM, cubic feet per minute. Okay, so we have cubic feet here divided by minutes. This is the abbreviation, it's a CFM, but it's not cubic feet multiplied by minute. Okay, be careful, it's cubic feet divided by minutes. So the total CFM, or the total air volume that we have to heat up, is 20 cubic feet, but per minute. it's not just, it's not 20, it's 200. It's not just 200 cubic feet. It's 200 cubic feet per minute. Okay, so because every time we are introducing fresh air, so every minute we need to introduce 200 cubic feet, which is a lot. It's a lot of fresh air that we have to introduce in a room. So that's why the air ducts are so big. What is the energy now? So we know that the energy was volume, or we can say airflow. And the units here, we are going to change the units because last time we calculated energy. Now we are going to calculate power, okay? So this would be power. Power is airflow, and the units of airflow, it's cubic feet per minute. But minutes are not, I don't like these units. I mean, the units of power would be, what is a unit of power in imperial units, by the way?
Is it BTU hour?
BTU hour, correct. Who are you, sorry?
Allison.
Allison, okay, great. So this is BTU per hour. Okay, so we need hours here. We have minutes, but we need hours. So how can we turn minutes into hours?
Wait, I have a question.
Yes, sure.
Why did it say energy before and now it says power?
Yeah, because we can calculate this in two different ways. We can calculate energy, or we can calculate power. Last day, or on Tuesday, we calculated energy. Today, we are going to calculate power, because I want to show you how to, because we need to move from power to energy very quickly. Okay, so today we're going to work with power, and then we will move to energy. On Tuesday, we calculated just the energy. Okay. We can make the same exercise with power or with energy. The only thing is that we need to be aware of the units. If we are calculating energy, this is just BTU. If we are calculating power, this is BTU hour. And the airflow, last time it was just cubic feet, but now we need to divide the volume. We have to divide by the unit of time. In this case, we have minutes. But this is not enough because we need hours here. So we have to multiply this by 60 minutes per hour. And now we can cancel minutes, okay? And we will end up having a cubic feet per hour. And because now we need here BTU per hour, okay? So what's next? We need the enthalpy, the difference of enthalpy. So I wrote it down. So the enthalpy was 24.5, the indoor enthalpy, minus 9.4, the outdoor enthalpy. What are the units of enthalpy? The units of enthalpy are BTU divided by pound. Okay? So now I'm going to make something else. Okay, I think now it's clear. So this is airflow times 60 minutes, because now we need to introduce time here, and we need hours because the power is BTU per hour. This is the enthalpy, and the units are BTU, and then we have to divide this by the specific volume. The specific volume is 13 cubic feet per pound. Okay, so the outdoor specific volume was 12.5, the indoor specific volume was 13.5, so the average is 13. Okay, so it can be 13, 13.1, 12.9, I don't mind, but it has to be something close to 13. So this is the, well, this is it. Okay, so this is the power. So if I solve this, the airflow is 200. The enthalpy is this, and I have to divide this by, so this is 200 times 60 times 24.5 minus 9.4 divided by 13. Okay, so this is around 13 power in BTU hour equals 13,938 BTU hour. Okay, so this is the power. So this is the size of our burner. Okay, so when we are, if we go to the Home Depot, okay, I want a burner. Okay, what burner? First decision, what you want to burn? Oil, gas, pellets, wood, coal. So that's the first decision. There's a so the first decision is what kind of fuel you want to burn. Okay, we see that pellets are a good option. Condenser gas boilers, it's another good option. And the second is what is the size of your burner? Okay, so and the size is not the physical size, it's the power. Okay, so I need to well, the heating loads are 13 or almost 14,000 BTU hours. So my burner, it has to be more than 14,000 BTU hours. It can be 15, 16. It depends. You are not going to find a commercial burner with 13,938 BTU hours. It's possible. You will find, okay, this is 14,000 or 15,000 or 20,000, whatever. But the burner you are selecting has to be above this value, because this is the actual value that you have to that you need to heat up this this air. Okay, so this is what we have done. With those figures, we have made a lot of decisions. Okay, so let me write this down. The power is 13,938 BTU hours. The airflow is 200 CFM. Okay, and now I will stop sharing my screen. And I'll start sharing this one. Okay, here we are again. So now we know a lot of things of this about this system. We know that the burner, the power of this burner is 13,938 BTU hour. Okay, yeah. So this is the size of my burner, of my boiler, or whatever. I know that the flow of the air handling unit is 200 CFM. And well, and that's it. Okay, so I can go to a shop, to a mechanical system shop. And okay, what do you need? I need an air handling unit and I need a burner. Okay, what kind of burner? Condenser gas boiler. Okay, perfect. A condenser gas boiler. What size? I need 13,900 BTU hours. Okay, we have this one, which is 15,000. Okay, I'll take this one. And what about the air handling unit? Well, I need the airflow of the air handling unit should be 200 CFM. Okay, I have here this air handling unit for you. We're done. Okay, so now we have solved a real problem, a real issue in our. So this is okay. So now you can design and you can specify what mechanical systems you are using. Okay, so what do you need? If we have a boiler, we need to specify first the fuel and second the size in terms of power. Perfect. Then you need an air handling unit. Well, you need to specify the airflow of this air handling unit. And the airflow depends on the number of people because we had 10 people here. Okay. And this CFM is something that every single building, we will need around 20 CFM, cubic feet per minute, and per person. So that's it. Now we know a lot of things. And what else? Okay, now we have to turn this power into energy. And how can we do that? Okay, so look at this. The power, this is too artistic. Power is 13,938 BTU hour. Okay, so now how much time is the we need to know the schedule of the building. We can say it's this building, it's operating from 8 a.m. to 8 p.m. So it's 12 hours. Okay, so the energy equals power times time. So if the power is 13,938 times 12 hours, that would be times 12, 167,261 BTU. This is the energy. Okay, so that's why we can either calculate energy if we enter in that formula with the air volume. Okay, so we can calculate again. Well, energy is the air volume times the difference of enthalpy divided by specific volume. Power equals CFM, cubic feet per minute, times 60, because this is a minute per hour, times enthalpy divided by specific volume. Okay, so the energy is BTU, and then the power is BTU power. If we want to go from power to energy, we have to multiply this by the time that the system is operating. If we are operating the system for 12 hours, this is 12 hours. If we are operating the system for 24 hours, that would be 24. Any questions about this?
No.
Okay, because I didn't know that you were listening to me. Okay, great. So you have now. What do we have to do? First, we have to understand the problem, and this is the problem. Okay, so the problem is this: there's a room. We have a room here. This is the room. There are people. People are sweating, are releasing water. We have to get rid of that water. How can we do that? We can do that with the air handling unit. Okay, so we need the air handling unit. But the air handling unit, it's something that can be connected to a burner or a boiler, something that heats up water. Okay, so if this happens, then this is the system. So here I control temperature and I control relative humidity with the air handling unit. So that's great. Now we need to specify what burner we need, and I have to calculate the power. To calculate the power, I need the amount of air that I need to supply. So the amount of air, it's always 20, and depends on the number of people. If we have 10 people, this is 200 CFM. With that CFM, with the difference of enthalpy between the outdoor conditions and the indoor conditions, then we calculate the power that we need. If we need the energy, then we can calculate the energy. Okay, with this number, this is the power, and this is the time. So I need to, well, but this is up to the client. I mean, architects, we don't decide the schedule of the building. It's if Keene State College wants to run the TDS center from 7 a.m. until, I don't know, and then is it open the weekends? We don't know. It depends. Okay, so the schedule of the building, it's a decision of the client. So we have to ask what the schedule of the building is. If it's every day from 8 a.m. to 8 p.m. and we don't have this on the weekends, so that will run only for 5 days, for example. Okay, this is not our decision. We have to talk to the client. When we know this, we calculate the energy. Okay, so we have the power, and how many hours is the system running? 12 hours. Okay, so I multiply the power times the time, and I have the energy. And energy, it's interesting because energy is what we paid for. Okay, so our electricity bills or the utility bills or the energy bills, they specify energy. Okay, so they don't specify power. So when we are, it's the energy that we can have a boiler or a heating system with a high power, but depending on how many hours we are running this boiler, we can pay more or less money because we are paying in terms of energy. We are not paying in terms of power. So we always tend to oversize the power of the boiler or the heating system because it's like cars. Okay, if we have a car that can run at 200 miles per hour, if we are running at 100 miles per hour, it would be more efficient. So we always tend to oversize the power of the heating system. We cannot go too high because there will be other issues. Okay? But we always tend to oversize the power. So if 13,900 is the actual power, okay, it can be 15, 16, 20,000 maximum, but no more. We cannot have a 100,000 BTU hour boiler because it won't work well. So it can be slightly above that the actual power that we need. Okay, so this is it. What else we can do? Okay, so now we have to work with different units, and now we have to start talking about schematics. Okay, so now we have different options, and we have to connect those options, and then we have to prepare schematics of building. So let's do it. So first are the options that we need. So what are the options? Let's say that we have an air to water heat pump. Okay, this is the first element. The second element is a tank, let's say a buffer tank. The third element is it's an expansion tank. The fourth element is a circulating water pump. And finally, we need a radiant floor. Okay, so we have all these elements. And now we have to classify these elements in terms of what they do. So the air-to-water heat pump is the energy production. Okay. The radiant floor is the, what do you call it? It's the terminal unit. Okay. And all these things, the buffer tank, the expansion tank, and the circulating water pump, well, those are things that we need in this mechanical system. But well, we need this circulating water pump to circulate water. We need expansion tank to release if there's too much pressure in this piping system. We need an expansion tank. And the buffer tank, it's something that we need to store energy. Okay, but we always need energy production, and we always need a terminal unit. Then we need more elements, but those are the most important elements in a mechanical system: the energy production and the terminal unit. We have the air-to-water heat pump, so it's a heat pump, so it runs on electricity, and we need a radiant floor. So that means this works with water. So radiant floor works with water. So this water here is the water that we have in the heat pump. Okay, so we are heating up water in the heat pump, and then we are releasing this heat through the radiant floor. Okay, so those are the components. Now we have to work with those components. So let's do it. So first, the heat pump. the air to water heat pump. It's outdoors. Okay, so we have a box like this. This is the air to water heat pump. And we are heating up the water. So we need an air water inlet. And we need a water outlet. Like this. Okay, so that would be not cold, but warm water, and that would be hot water. And here we are heating up the water inside this box, which is the heat pump. Okay, this is an air-to-water heat pump. So remember that if we are using air, that air means that the heat pump is outdoors and it's in contact with air here. Okay. But on the other side, we have water. So through these pipes, we have water. Okay, so that's why we have the air to water heat pump, because this is outdoors, it's in contact with air, and it heats up or cools down, but it works with water. Okay, so what's next? We have the buffer tank. So the buffer tank is something that is between the air energy producer, which is the heat pump, and the terminal unit, the radiant floor. So we can work with the buffer tank here. And I'm using two colors. Okay, so we are merging the colors here, because that will actually happen in that buffer tank. Okay. And then we need so this is something in the middle between the terminal unit and between the heat pump. And then we need the radiant floor. Okay, so the radiant floor, we need the outlet here. Okay, usually the radiant floor, it's an spiral like this. Okay, so we circulate hot water, and then we release that heat, and then we have another pipe like this. Okay, so we circulate hot water, that radiant floor releases heat. Indoors, and then the water cools down, and then we have to go back to the buffer tank with water that is not as hot as this one. Okay. What else did we have? We had expansion tanks. Okay, so the expansion tank is something that, well, we need expansion tanks always here. Okay, when we have a closed loop, we would need an expansion tank. So I would place two expansion tanks here. So one before or between the heat pump and the buffer tank, and another between the buffer tank and the radiant floor. Okay, so I would name this as expansion tank, ET. And then we need circulating water pumps. So the circulating water pump is something that moves water. So here we have to move water from the heat pump to the buffer tank, and then we have to move water from the buffer tank to the radiant floor. Okay, so we would need two circulating water pumps. So a circulating water pump is like a rectangle, no, sorry, a triangle like this. Okay, it's a circle with a triangle, and this is the sense of the flow. So if we are moving the water in this direction, so then this triangle has to go in that direction. Okay. We always need a legend, okay? Whatever we are doing here, if we use symbols, we need a legend. So if this is the water pump, and if this is the expansion tank, okay? Are we done? Not yet, because with this kind of thing, we can do even more. Okay, so that would be the most simple heating system if we have a house. Okay, so we have this air to water heat pump. Then we need the buffer tank. And why do we need the buffer tank? Well, because we need to store energy. Okay, so these kind of pumps, heat pumps, if they start and they stop continuously, this is harmful for the heat pump. So the heat pump needs to work for, let's say, a couple of hours. Okay, so we need to increase the amount of water that we are heating up. So that's why we need a large amount of water, because the amount of water that we have in the radiant floor, it's not that much. So if we had only the water on these pipes, the heat pump will be starting and stopping continuously, and this is not good. So that's why we have a buffer tank. So this buffer tank has a, let's say, 100 or 200 gallons, and then it takes time. It takes a couple of hours to heat up this water. But it takes a couple of hours to cool down that water. Okay, so the heat pump is working for 2 hours, and then it's not working for 2 hours. And this is better than, okay, I have the heat pump is working for 5 minutes and then it stops. 5 minutes and stop. 5 minutes and stop. It doesn't work. Okay, so we need this buffer tank, because by heating up this buffer tank for 2 or 3 hours, the heat pump works better. And what else? Well, with this system, we can do something else. We can provide hot water for the house. Okay, so if we have an air-to-water heat pump, we have a buffer tank, and we have this heating system, but we need heating and we need domestic hot water. Okay, so we need hot water. We open the tap and we need hot water. Okay, so for this, we need a cold water supply for the buffer tank. Okay, so we can call this cold water supply. And then we need to connect this to what? We need to connect this to a shower. Let's say we have a shower, and here we have hot water. Okay, so the position of those elements are not, we need to think about it. Because as we know, the hot air, the hot water tends to go up. So if we are heating up this tank, the hottest water will be on the top here of the buffer tank, because the hot water tends to go up, and the coldest water would be here at the bottom of the buffer tank. So that's why if we need to supply cold water, we need to supply cold water from the bottom. And if we need to supply hot water, we need to take this hot water from the top of the tank. Okay, so this is not, we cannot take the hot water supply at the bottom of the tank and the cold water supply at the top of the tank. It won't work at all. Okay, so if we need to supply cold water, sorry, this is blue. If we need to supply cold water, we need to supply this water at the top of the tank. And if we need to release hot water, then we need to release hot water here. Now we can talk about temperatures. Okay, that's another interesting question, because we have hot water, cold water, but we need to put figures on that. So what is the temperature of hot water in the shower? What do you think?
80 something.
Sorry?
Like 80 something degrees.
80 something. What is the temperature of the human body?
97.
Again, I don't hear you.
97.
97. Okay, so the human body here is at 97. So do you think when you open the hot water, is it hotter? Is it or colder than your body?
Probably hotter.
I'd
Yes.
say it's like 100 or like 110.
Yeah. Just gotta be a little
110.
bit hotter.
Okay, well, there's a limit of hot water we can bear. I mean, we can cope with, because if it's 200 Fahrenheit, probably we will get burned and we will die. Okay, but when we open the hot water, yeah, we feel that it's hot, and if our body is at 97, so it has to be hotter. What is the temperature of hot water? Okay, so let me. I'm Googling now. Okay, 60. Well, the temperature for hot water, I mean the hot water that we feel in the shower, is around 140 Fahrenheit.
140?
140.
Damn.
Yeah. Well, 140, it's too much. I mean, if you are under 140 for a couple of minutes, you will die. So you mix you open the cold water, the hot water, and yeah, we mix cold and hot water, and we end up having something close to 97. Okay, so if our body is at 97, yeah, so someone told before 110, yeah, kind of. Okay, but 110 is the temperature, is the mix between cold and hot water. But the official temperature that we have to provide, so here at the top of the tank, the temperature has to be 140. Why? Because there are some bacteria that we have to kill. And this bacteria is the Legionella. Okay. Well, there is this kind of bacteria. We kill that above 140 Fahrenheit. Below 140 Fahrenheit, between 100 and 130, this bacteria lives well, and it's a very dangerous one. Okay, so we have to be careful with that. So that's why if we have this kind of installation, and if we are in contact with hot water, we have to make sure that somewhere in the system we have killed this bacteria, and we kill the bacteria at 140. Okay, so on this tank we need 140 Fahrenheit, and then we can apply cold water, and we end up having 110 because our body is at 97. Okay, so that makes sense. But if we just open the hot water without opening the cold water, the temperature should be around 140, because we need to kill this guy. We need to kill this Legionella. Okay, so this is the temperature. So the temperature here should be 140. What about the temperature in a radiant floor? So we have different pipes running, the water is running through pipes that are underneath the floor we are stepping. So what do you think, what is the temperature through these pipes in the radiant floor? What do you think?
Is it 140?
No. 140 is too much. Too much. If we have, well, 140, it's too much for a radiant floor. If we are talking about radiant floors, yeah, here it can be like 100 Fahrenheit. Okay, because what is a radiant floor? A radiant floor, this is the flooring. Okay, we can have tiles or whatever. Then there are water pipes here. Then we have thermal insulation. So we can use the thermal insulation here. And finally, we will have the floor slab. Okay, something, this is the, this is a typical detail of a radiant floor. So we have those pipes. Through the pipes, the hot water is running. Then we have a flooring. It can be tiles, it can be ceramic, stone, wood, whatever. So we are releasing the heat upwards. And why are we releasing heat upwards? First, because heat or hot air tends to go up. And second, because we have the thermal insulation here. So this thermal insulation layer prevents heat from going down as well. Okay, so we are releasing this. And we are stepping on that floor. Okay, so this is the food. Okay, so this is the effect of the radiant floor. It's a very comfortable effect because our feet are warm and the head is cold. If we have hot head and cold feet, this is terrible. But the other way around is the right thing. Okay, So we keep our feet warm, and the hot source is far from our head. So this is the most effective way to heat up space.
Do heated driveways work the same way?
Driveways. You mean for, yeah, kind of, but okay, driveways, well, I'm from Spain, so we don't heat up driveways. But I can understand that in New Hampshire you have to heat up the driveways because you have to melt the snow. This is what you mean.
Like for the driveway, do they still put like all the water pipes and stuff underground, or is there a different process that they do?
No, it's like this. I mean, I'm sure they are using hot water because they want to melt the snow. This is what they want in driveways. Because if it snows, if you want to drive your car, yeah, so in some cold countries, they have, in Northern Europe, in Norway or Sweden, they have this kind of radiant floor even in sidewalks, okay? So because it's snowing, and if you want to walk down the city, you need to melt the snow. But it's the same. We are using pipes, water pipes with hot water. Yeah, so that's the radiant floor. But we're not going to study that. We're going to apply this only for houses. I don't know the temperature in driveways, but the system is the same. We have pipes with hot water on it. Probably there will be a thermal insulation underneath the pipes, and then we will have a flooring. So yeah, so it's the same thing, but I mean, it's the same concept, but I'm sure that the size of the pipes, the temperature of the water is different than in houses. But this is a radiant floor, okay? So this is the flooring. Those are the pipes. This is the thermal insulation. And this is the slab. So this is a structural element. Okay, so at the end, I can have, let's say, at least one foot. Okay. So if we are using radiant floors, the space that I need is at least we need one foot for the flooring, the pipes, the thermal insulation, the structural slab. Okay, so it's something thick, but it's very comfortable. Okay, so in terms of heating systems, especially for single-family houses, this is the best option. We can use radiators. Okay, so we can use radiant floors, or we can use radiator. A radiator, as you know, well, it's something. We have a box like this with a grill, and in a radiator, we have like a hot water pipe, and then we have like elements, plates like this, and this is within a box. Okay, so there's a box like this, and we have a grill here, and that's it. So the hot source is within that element. So this is a radiator. If you look at it inside, we have those this pipe, and then we have plates, and it releases heat. Okay, through these openings or through this grill, we release heat. And in radiators, usually they are placed somewhere in the room, but if this is the plan of the room, and we have windows. Okay, so if there's a window here and another window there, usually we have radiators placed just underneath those windows. And then we have to release the heat from the radiator to the rest of the room. This is a plan view, by the way. Okay. Someone told me that the temperature through radiators can be around 100 and also through radiant floors was 140. This is not true, but through radiators we can have even 140 or above. Okay. Why? Because we are not in contact with this water. It heats up air and then it releases hot air through that grill. But we don't touch that water. So that's why first we have a point here, and this small element has to heat up the whole room. Okay, so that's why we need to increase the temperature of water here. The good thing of radiant floors is that the temperature of water can be around, let's say, 90 to 100 Fahrenheit. It's good enough. So we save energy, okay? Because with radiators, we have to heat up water up to 140. With radiant floors, we have to heat up water up to 90 or 100 Fahrenheit. So that's another way to save energy. So it's more comfortable because we distribute the temperature evenly or the heat evenly. We save energy because the temperature of water is lower. So there are a lot of advantages in radiant floors over radiator systems. But anyway, if we are looking at this system, we need a heat pump, we need an expansion tank here, we need the radiant floor, and then we can provide the house with hot water for showers or whatever. So that's it. This is the easiest way to heat up a house. Instead of a heat pump, we can have a burner. We can have a gas condenser gas boiler. We can have a pellet boiler or whatever. Anything that heats up water, we can have it here. If we are using the heat pump, we have to understand that this runs on electricity. Okay, so we need electricity to run the heat pump. And then we need those circulating water pumps to circulate the water. Okay, so this is it. What do we have to do now? Well, first, I'll stop sharing this. Okay. So what I'm going to do, I'm going to upload an assignment, and you will have to do something like this. Okay, so you will have to calculate the ventilation load. I will give you the number of people that we have in that room. So you have to calculate the total CFM, and then you have to calculate the power, and I will give you a schedule of the building. So it opens from 10 a.m. to 3 p.m., whatever. And then you will have to calculate the energy, okay? So it's always the same. We need the number of people. With the number of people, we have the ventilation load. With the ventilation load and the enthalpy, we can calculate the power, and with the time that the building is running or operating, we can calculate the energy. Okay, so I will upload an assignment, and then you will have to calculate this. It will be very easy, and it'll take 5 minutes, but I want you to become familiar with that. And then I will assignments. Not. There you go. Okay. I will provide you with this. This is what we have done today. Okay, so we have the air-to-water heat pump. This is the expansion tank. This is the circulating water pump. This is the shower, and this is the radiant floor. Okay, so we can do this with PowerPoint. We have the expansion tank. So with a PowerPoint, we know that we have to connect these. So we have to connect the buffer tank to the heat pump. Okay, so that would be the warm water. The expansion tank has to be connected here. Then we can also connect the water pump to the radiant floor. So from the radiant floor, yep, there you go. And finally, we need a shower. So we need to so that would be red and thicker. Okay, so we have to connect this to the shower, and we know that we need a cold water supply here, and we need circulating pumps. So at least we need a circulating pump here, and at least we need a circulating pump here, and we need another one there. Okay, because we have to move water in this loop, we have to move water in that loop, and then we need to move water from the tank to the shower itself. Okay, so that would be the same schematics, but with a PowerPoint. So keeping that in mind, the things that we can connect, I will provide you with something very simple, and then you will have to start working with PowerPoints because we need to become familiar with all these things. Okay, so I will give you different elements, and then you have to place the elements in the right position, and then you will have to connect those elements with arrow. Okay, so it's very easy. In PowerPoint, here you can click arrow, and then you can, here you can select the thickness, and here you can select the color. Okay, so we can have this one because this runs on electricity. Okay, so the heat pump runs on electricity, and so this can be the cold water supply, and that's it, because this is the expansion tank, this is the circulating water pump, this is the buffer tank, and this is the radiant floor. Okay, so this is the schematics. If you have the split outer unit and the split indoor unit, it's very easy because we only have to open another one. I will upload this chart on Canvas. So here, if you need a boiler, you can copy and paste that boiler. If you need an air handling unit or a fan coil, in this case, we need, what do we need? This one. We need the split outdoor unit and the split indoor unit. So that's a piece of cake because here we need to copy the split outdoor unit. Then we need to copy the indoor unit. Go. And then we have to connect it. Okay, so this is the schematics of this system. It's very easy because we have two units and they are connected with another loop. So we have an inlet and an intake and an outtake. So those are basic things that we have to know. And then we can combine things because we can have split units in our house. We can have a radiant floor. We can have a water-to-water heat pump. So we can have different things, especially if the building is very complicated, we will end up having different systems. So first we need the basics. So this is a basic system because we have the heat pump, the terminal unit, and the buffer tanks. With this system, we can have heating and hot water. Here, we don't have any hot water. This can provide us with heating and cooling, okay? And we don't have the hot water. So if we want to complete this house, we would need something for the hot water. So we will end up combining different things and we will end up using a lot of systems in the same building. But first we need to know this, okay? So here we have different names and we can connect, we can classify this by energy production or terminal units or ventilation. Then we have to connect, okay, so if we have ground source heat pumps, we can use radiators, we can use this, we can use all these elements. If we have split outdoor units, we only can use the split outdoor unit with the split indoor unit. And finally, we have the actual element here, the picture of the element, and then we need to connect things. And finally, we will combine different systems in the same house or in the same building. Okay, so this is what we're going to do. And we will talk about these schematics next week, but what the assignment will be on calculation of the heating load or the energy or the power that we need for the air handling unit.